Hi there. In this video we're going to talk about domain and range of functions. So when we have a function, we know that it accepts an input and it produces an output. Well, the domain is the set of possible inputs. So as we said before, you can think of a function as a machine. It takes one thing, produces another thing. So if we're thinking about like a candy machine, what are the set of inputs? What are the things that you can put into that candy machine? Well, you can put in coins. You can put in maybe a $1 bill, $5 bill, $10 bill maybe. That's the domain. It's the set of stuff that it accepts. Now, try to feed in a $100 bill, probably isn't going to accept that. I don't think many candy machines do. Can you put in a head of lettuce? No, it's not going to accept that, right? So there are things that aren't in the domain of that function. So the things that are in the domain, coins, $1 bills, $5 bills, $10 bills, maybe a credit card. The newer candy machines do that, right? So that's the domain. It's a set of inputs. Now, mathematically speaking, how would we say this mathematically? Well, we would say the domain is the set of numbers x such that f of x is defined, right? So we have that function f, and we're just saying that the domain is all the stuff that you can put into it and get something meaningful out. The other thing associated with functions that's very important is the range. Well, if we just talked about the set of inputs, that's the domain. Well, the range is the set of all outputs. That's all the stuff you can get out. So think about the candy machine. What can you get out of the candy machine? Well, it's all the candies that are in the candy machine. That's the range. There are things you can't get out of the candy machine, right? You can't get a tube of toothpaste out of a candy machine. You can't get a giraffe out of a candy machine, right? So those things are things, but they aren't in the range. So mathematically speaking, what we would say is that the range is the set of all values f of x where x is a number in the domain, right? So something x is in the domain, something you fed in, f of x is what you get out. So it's describing the set of all outputs. So just very quickly, a quick way to think about it is that the domain is the set of all possible inputs. The range is the set of all possible outputs. So let's do some examples and take a look at how to compute the domain and range for some specific functions here. All right, so here we have a function f of x equals x squared. Let's see if we can think about what its domain is. So what am I allowed to plug in to this function that would produce an output? So what numbers can I square and get an output? Well, I could square 1, 2, 3, 4, any number between those numbers. So any positive number works. You know, if I square those numbers, I get a meaningful number. 0, you could square 0. 0 squared is 0. I know what the answer is, so it's in the domain. What about negative numbers? Can I square negative numbers? Sure. You can square negative 3, you get 9. Square negative 5, you get 25. It doesn't have to be integers. I could square negative square root of 2. I could square negative pi, right? Any number, in fact, I can square. So what that means is that the domain is the set of all real numbers. We say real because sometimes in mathematics we talk about other types of numbers like complex numbers, which are an extension beyond real numbers. But in this class, unless we say otherwise, we're going to be focusing just on real numbers. And so this is saying it's all the real numbers. That's one way to write it. Another way to write it down that would also be correct is to describe the domain as an interval. An interval is a range of numbers between two values. Well, if it's all real numbers, we're going from negative infinity all the way up to positive infinity. So that is the interval. Interval negative infinity to positive infinity. Another way to write down the domain is using what's called set builder notation. And set builder notation, what we do is we describe what it means to be a number in the domain. So it's going to be the set of things, set of numbers x, such that, this vertical bar denotes such that. Sometimes people will just write a colon, but very often they'll write a vertical bar here. So it's the set of all numbers x such that, now I'd put a condition on x. Well, the condition is just that x is between negative infinity and positive infinity. So that's what I write. X is greater than negative infinity and less than positive infinity. And then I close the set. This open bracket, we begin the set, and then this close bracket closes the set. So whenever you use set builder notation, you're going to have an open bracket and then a close bracket. And in between is a description of what's in that set. So that's the domain. It's all real numbers. 3 different ways to write it. What about the range? What numbers can I get out of this function? What are the outputs? Well, here it's not everything, right? Because if I start squaring numbers, I realize that when you square something, you never get a negative number, right? If we feed in a real number as an input, we'll never get a negative number as an output. If you square -3, you get +9, right? You always get a positive number. Or if you square 0, you do get 0. So you could, not just positive numbers, but 0 as well, so non-negative numbers. So that's what I would write. All non-negative numbers. That's the range. Or if you wanted to use interval notation, I would write it's the interval from 0 to infinity, including 0. Right? So I put a square bracket around 0 to denote that 0 is included in this set. If I wanted to use set builder notation, I could write the set of all numbers x such that x is greater than or equal to 0. There you go. That would be it in set builder notation. You should be familiar with all 3 different ways to describe a set, because sometimes one of these ways is easier than the other one. Sometimes it's very hard to describe a set in words, but it's not so hard to just use some intervals. Sometimes the set's not easily defined in terms of intervals, and it's actually easier to write it down in terms of some inequalities. And so in that case, you'd use set builder notation. So let's take a quick look at a graph of f of x. Here we are. This is a graph of x squared, and we can see that for any number x down here on the x-axis, there is a graph above it. Well, if there's a graph above a value of x, that means that that value of x is in the domain. And since every value of x has a graph above it, we know that the domain is every real number x. Now, what about the range? Well, the range are the set of values on the y-axis. They're the set of outputs. Notice that not every number on the y-axis has a graph next to it, right? Only the numbers that are 0 and up have a graph to the left or right. So only those numbers are in the range. So we can see the domain by considering which numbers x have a graph above or below them, and which numbers are in the range by considering which numbers y on the y-axis have a graph to the left or to the right. And so this validates what we wrote for our domain and range. The domain is all real numbers for x, but only non-negative numbers for y. Okay, let's go to the next function here. Here we have a function square root of x plus 3. So what's in the domain? Well, you have to be careful here. I'm taking the square root of a number. Now remember, in this class, we're focusing on real numbers. So what can you take the square root of and get a real number answer? Well, I can take the square root of 1, right? I get square root of 1 is 1. I can take the square root of 4, I get 2. Can I take the square root of 3? Sure. Square root of 3 is it's an irrational number, but it's a real number, right? So that's fine. I can take the square root of 3. Where do I run into problems? Well, I run into problems when I try to take square roots of negative numbers. If I take the square root of -2 or -4 or -1 or negative pi or negative anything you want, -8/9, those things aren't defined as real numbers. They actually are defined as imaginary numbers or complex numbers, but we're not dealing with those in this class. So as far as real numbers goes, negative numbers don't work, right? So the domain, it can't include negative numbers. Is there any other problems with this? Anything else it can't include? Well, no, that's the only problem. As long as x is a non-negative number, I can compute this, and then whenever I've got a number, I can always add 3. That's not going to pose any problem there. So the answer here is that the domain is all non-negative numbers. Got to work on my handwriting there. All non-negative numbers. All right. Or in interval notation, we could write it like that. Or in set builder notation, I could write x, instead of all numbers x, such that x is greater than or equal to 0, right? Now, what about the range of this function? What are the possible outputs that I can get out? Well, what's the smallest this thing can be? Well, the smallest this thing can be, remember, I'm not allowed to plug in negative numbers for x, but I can plug in 0, right? And the square root of 0 is 0, and if I add 3 to that, I get 3. That's the smallest this thing can possibly get, is 3. And that happens when I plug in 0 for x. So we know the range is going to start at 3 and go up from there. How high does it go? Well, I can plug in different numbers for x bigger than 0 and get numbers bigger than 0 as the square root. Right? But plug in a larger number and the square root of that is a larger number. There's no limit to how large this can be. And so when I add 3, there's no limit to how large that can be. So the range is the set of all numbers 3 and greater. All numbers greater than or equal to 3. Or, if we want to write that as an interval, it would be the interval 3 to infinity, including 3. Or in set builder notation, I would write the set of all x such that x is greater than or equal to 3, right? All right, let's take a look at the graph of G. Here it is. And you can see that not every number is in the domain. Not every x has a graph above or below it. In fact, the graph only starts once we get to 0. So that's why the domain begins at x equals 0 there. But as I go to the right, every other number x, every number to the right of 0 is in the domain. Every other number to the right of 0 has a graph above it. Now, what about the range? Well, the range is determined by looking at the y-axis, and we see that we don't have a graph to the left or right of y values until we get to 3. So that's why 3 is the starting point for the range. But then every number above 3 does have a graph to the right. So every number 3 and up is in the range. Okay, let's extend the camera down a little bit. Not that far. Okay, let's look at our next function here. H, the function h is given by the square root of x plus 3. Notice this is different than the last one because the square root includes the plus 3, whereas before it didn't. So this is a different function. Let's see what that changes about things here. Well, what can I plug into this function? Well, remember what was important is that we can't take the square root of a negative number, right? So we have to make sure that x plus 3 is not negative. In other words, what we need is we need x plus 3 to be positive. Well, okay, if we need this, I can solve this for x. Subtract 3 from both sides. And I see that x has to be greater than or equal to -3. Well, as long as that condition holds, I can compute this, right? Then I know the input, x plus 3, won't be negative. So I'll be fine. So that's the domain. The domain is the set of all numbers greater than or equal to -3. As an interval, I would write it like this. As set builder notation, I would write it like this. Okay, what about the range here? Well, what's the smallest this thing can be? Well, the smallest this can be is where the input is as small as it can be, the thing under the square root. The x plus 3, how small can that be? Well, we said it couldn't be less than 0, right? Because otherwise it wouldn't be in the domain. So what would make this 0? Well, this is 0 when x is negative 3. So the smallest x can be is negative 3. And square root of this when x is negative 3 is the square root of 0, right? So that's the smallest it can get. So the range is a set of all numbers greater than or equal to 0, all non-negative numbers. Now, how would I write that as an interval? It would look like this. How would I write that in set builder notation? The set of all x such that x is greater than or equal to 0. Okay, let's take a quick look at the graph of our function h. Here we see it here. The domain is the set of all values on the x-axis that have a graph above or below them. And we can see that, well, there is no graph above any value until we get to negative 3. But then once we pass negative 3 and go to the right, all those values have a graph above them. And so the domain we can see here is negative 3 to infinity. Now what about the range? Well, the range, we look at the y-axis, and we look at all the values on the y-axis that have a graph to the left or the right. Well, we don't start having a graph until we get up to 0. And then once we get to 0 and up, we have a graph to the left or right, right? So the range is the set of all values 0 to infinity. Okay, let's go to the last function here. All right, through the magic of video editing, I made a quick change to this problem. I also fixed some of the shadow issues that we were having here. So this is the one we're gonna look at. Okay, so here's r is given by this expression here. All right, so we need to find its domain. Okay, so for this problem, I think it's easiest to think about what is not in the domain. What could go wrong here? Well, you know, x minus 1 squared, I can plug anything into that. That's fine. Plug any number in for x, and I can compute x minus 1 squared. No big deal. But what is going on with that? I'm dividing by it. What do we have to be careful about when we divide? 0. Yes, division by 0. You're right. Cannot divide by 0. Division by 0 is undefined. So we just have to make sure that what's in the denominator here is not 0. Well, can it be 0? Sure, when x is 1. And that's the only way it can be 0. So the domain is the set of all numbers except 1. All real numbers except 1. How would I write that in interval notation? Well, I can go from all real numbers, all negative numbers, from negative infinity up to 1. And I can go from 1 all the way up to infinity. All those numbers work. And I want to consider these two sets together, this one and also this one. So the symbol we use is called the union symbol. And it looks like a U. But don't write a letter U with a little with a little tail here. Don't write that tail. It's just a curvy cup shape. That's the union symbol, and it means to combine the two sets and consider them as one. How would I write this in set builder notation? Well, it's the set of all numbers x such that x is not equal to 1. So here's a situation where I think set builder notation is actually the quickest way to write it. What about the range here? What's the range of this function? Well, let's see. Can I ever get, is there any numbers I can't get as an answer here? Well, if you think about it, 0. There's no way I can get 0, right? There's no number I can plug in for x and get 0 as an answer. You can't divide 4 by a number and get 0. Anything else? Well, if you look at this, the denominator is squared, so it's always non-negative. And I'm dividing a positive number by a non-negative number. That means I'm always going to get a positive number, right? I can't get anything but a positive number. Now, what positive numbers can I get? Well, if x gets really big, this number down here gets really big, right? A big number minus 1 is still a big number. A billion minus 1 is still a big number. Square it, big number, right? What happens when you divide by a big number? 4 divided by a billion. It's a tiny number, right? When you divide by a big number, you get a tiny number. So this can get very close to 0. Can never get to 0, but it can get very close to 0. Okay, so all numbers above 0 and up to, how high can they go? How big can this get? Well, how can I make this thing large? Well, you can make a large number by dividing by a small number, right? If you take 4 divided by 0.1, you get 40. 4 divided by 0.01, let's make the denominator even smaller, I get 400. 4 divided by 0.001, I get 4,000. The smaller the denominator gets, the bigger this gets, right? The bigger the whole thing gets. So I can make this as big as I want just by making the denominator small, and I make the denominator small just by letting x be close to 1, right? So this can be as close to 0 as we want, and it can be as big as we want. So the range is the set of all numbers from 0 to infinity, all positive numbers. Went off the screen there. Let me zoom out. All positive numbers. As an interval, that'd be the interval 0 to infinity. In set builder notation, it would be the set of all x such that x is greater than 0. Okay, let's just take a look at the graph of our function r. Here we can see it here. The domain is the set of all numbers on the x-axis that have a graph above them or below them. We can see that every number up until we get to 1 has a graph, above it, right? There will be a graph above all those numbers, but not above the number 1. And that is why we wrote our domain was the set of all numbers except 1. And what about the range? Well, the range, we look at the y values and see which y values have a graph to the right or left. Well, we see that down here below 0, we don't have any graph to the left or right of these numbers. But once we get to 0, well, 0 still, the graph never actually gets down to 0, so 0 doesn't work. But once we get above 0, then we have a graph. So the range is the set of values from 0 to infinity.